Okay, so the next speaker is going to be João Folhadela. He's got a master's degree from Porto University in physics engineering. He works in the hardware and software group of the Institute for AI Safety and Security at the German Aerospace Center. His research focuses on efficiently deploying AI models in specialized hardware like FPGAs for resource-constrained environments, including those in robotics, transportation, and the aerospace sector. And he's going to tell us a bit more about that work now.
Yep.
Thanks.
Thank you for the introduction. Actually, my first contact with FPGAs was like almost 2 years ago here at CERN. I had a workshop for experimental physics and was like this very small slot for a tutorial on how to light up a LED on a National Instruments board. And the guy basically said, okay, so with this tutorial, you basically can almost guaranteed land a job in FPGA. And 2 years later, here I am, so to present this work, so hopefully you like it. So I'll be presenting an FPGA implementation of next generation reservoir computing for predicting dynamical systems. So first of all, to introduce reservoir computing, you know that in classical machine learning, the most successful model would be the neural networks or fit-for neural networks, where the data goes through the network layer by layer. And here we see all the edges in this graph are weights, and all these weights are computed to train the network. On the reservoir side, we initialize randomly these connections between the nodes, and we actually also randomize the weights themselves and fix this. So this reservoir is fixed, and we only train the output layer, so only these weights are trained. So this is done via ridge regression. So basically, you want to minimize the loss, which is fine, just simply the squared error of the prediction with the real output value with some regularization parameter. Then you can say that the weight matrix is obtained by this equation here, which is an analytic solution. So it's usually much faster to compute than the much successful gradient descent. So this reservoir computing, as you can see, has been receiving lots of attention in the last few years with lots of publications on this topic and lots of new methods appearing as well. And what all these methods have in common is that they have some kind of nonlinear dimensionality expansion of the input data, and that they have the regression-based mapping onto the target data, as we saw previously. So for instance, one example would be like quantum reservoir computing, where the actual reservoir is a real physical quantum system where we pass some encoding through the quantum system, and then we read it and pass through this output layer on a classical computer, and we have some prediction. And this works quite well for some stuff. So, but here I'm focused on the next generation reservoir computing because it's a very efficient algorithm and it requires very few data points to train. So say we want to train on the Lorenz attractor. We want to predict the next time step of the Lorenz attractor. So first what we do is we take the x and the previous time step of x, then take the y and the previous time step of y, and also the same for z. And this forms our linear vector. And from this input linear vector, we want to expand it, do it some kind of nonlinear expansion, such as multiplying x with itself and x with its previous time step, and so on. So we do all the combinations in this linear vector, and from this kind of non-linear vector, which is of size 21, so all the combinations are 21. So then we concatenate these two vectors, and to get the prediction, so the next time step of x, y, and z, we simply multiply by the trained weights. So we do this in Python with NumPy's linear solver, so this is very easy, so it simply computes this equation here. And some parameters that we use just for reference is that we use only 400 training steps, and then we use two time steps, so the previous and the current time step, a regulation parameter of 9 times 10 to the minus 2. This, of course, will depend on how many time steps you have or how many train steps. And then the weight output shape is of the size of the reservoir, so 27 times 3, because we have 3 dimensions, x, y, and z. So then when it's trained, then we want to make the inference on the actual FPGA. So for that, we must first transfer the weight matrix and the first linear state to the FPGA memory, and implement also some kind of prediction loop to predict the successive time steps. And this prediction loop basically requires three parts. First, it's creating the reservoir itself, which is simply reading a linear state from memory and then performing the nonlinear expansion. So this is basically just multiplying and powering the linear state. Then we want to do the prediction itself, which is simply matrix multiplication. And here I implement it in a very naive way, which is several vector dot products and with multiply and accumulate units. And then we want to save this prediction to then prepare for the next prediction. So you see that all arithmetics are performed in float 32, and I implemented it with Vivado floating point IP for simplicity. It can be later, of course, much more optimized with some methods that were here talked about, and I'll be happy to read them later to try to implement here as well. And so basically this loop is implemented as a finite state machine where these three parts are basically here in these two states, on expand and predict and save. But first you have some kind of idle state, which just waits for the prediction to be started. Or if it's already in the prediction loop, then it expands. And from expansion, then it predicts and saves the result. And then it sends the result in some way. Here I implemented it with a UART, so it just outputs directly from the FPGA. And then we also have some cleanup state, which just resets all counters and variables. In specific, this expand state basically is implemented as a module, which expands a vector of size 6 into size 27, so the reservoir, and where we have that all multiplications are performed in parallel. And using the Vivado floating point IP, we use a multiply operation and full DSP usage, which means we'll have to use 42 DSPs for expanding this to the reservoir. And we use a maximal latency of 8 clock cycles. Then, in the end, when you get the reservoir, when you get the nonlinear expansion, you have to concatenate with input vector to get the reservoir and output it. Then the predict and save state basically performs the matrix multiplication of the reservoir with weights. And this is just 3 multiply accumulate units that are also implemented and are computing in parallel the result. And with Vivado floating point IP, it's just a fuse multiply add operation. I also use a full DSP usage, which means that we'll be using 12 DSPs and 10 clock cycles of latency are used, which means that in total for this operation, it takes like 270 clock cycles in total. And then in the end, we want to save the prediction to update next linear state. So here's the implemented device. We see that it doesn't cover that much area, and the resources are very few as well. The LUTRAM is how the weights are saved, and only the 54 DSPs which are used for the multiply and accumulate parts. Also, another report is on the power, so it's below the 300 milliwatt power. It's quite low, I guess. And clock speed, when you use a clock speed of 125 megahertz, we have worse negative slack of 1.3 nanoseconds, which means we have more room to kind of make the logic faster. So finally, here's the result of this simulation. You see here on the left, on red, the result, the prediction that came out from the FPGA. And on red is the 400 time steps that we use to train to predict the Lorenz attractor. And we see that the results are quite good. We seem to capture pretty well the chaotic behavior of the Lorenz system. But this is not enough, of course. We want to see point by point, because if we want a real application, then we require a perfect prediction. And this happens until the time step 300, and then it simply collapses, although we had the chaotic behavior. And of course, this can be improved a lot by doing other nonlinear expansions. And also, nothing that I've been researching is done continuous learning. So since the model is so easy to train, once we do, say, 200 time steps, then we retrain the model with the new data. And that gave some quite good results, and hope to publish this soon. We can also compare it to double precision on a CPU, but of course, there's no difference at all. So also another question would be to research into how much can you quantize the model until it performs much worse. And I had some preliminary results with 8int, but that's not ready to see. But yeah, it's a work in progress. So here's another comparison that I did with the CPU. So basically, this is implemented in Python using NumPy with a clock speed of 4.8 gigahertz. Inference time, it's 50 microseconds, while on FPGA, it's only 2.5 microseconds at 125 megahertz. This was measured from the simulation in Vivado. So yeah, I think it's much faster. So we say that this indeed is a very easy to implement algorithm. It is low power, and it's fast. So, but of course, this is to predict a Lorenz attractor. And in real situations, we don't want to predict it. We want to predict real things that are happening. And we see some growing research on this. And I'd like to highlight this publication in Nature in 2024 by Kent et al., where they use this model, I mean, even a simpler model, which is used to control this chaotic circuit, which had some kind of perturbed chaotic dynamics. And they're able to, with the next generation reservoir computing algorithm, bring this dynamics to some kind of controlled behavior. Another topic that's been researched is on energy demand forecasting, for instance, where you see that reservoir computing predicts quite well the heat demand on a home. And then there are, of course, financial markets, weather, coastal line erosion, robotic control, and some of these topics are also a part of our research in our institute. So I hope I incentivize you to look into reservoir computing because it's very simple before looking to huge networks like neural networks, transformers, whatever. If you have a simple problem, then this might be able to solve it. So thank you, and any feedback is very welcome.
Thanks. Very interesting talk. Are there any questions? Yeah, Davide.
Hi, very nice talk. So I'm curious, so with your FPGA, you try to run with a clock speed of 125 megahertz, but this limitation is due to the fact that then you don't meet timing, or did you try to push the limit harder? Or?
I did some experiments, and like I was using faster clocks, but then it also I have to play around a lot with the floating point IP, with the clock cycles, and this will take a lot of time to implement and so on. So I just decided to stick with 125 because it was easier, and then, yeah.
Do you have also benchmark against the GPU, perhaps?
No. I mean, this is very simple. I don't think like GPU would be overkill for this kind of algorithm, I guess. We're also looking to Pi Pico, for instance, Raspberry Pi Pico, and it could also work for some instances, yeah.
Right.
So can you go back to the evaluation where you show the simulated versus the predicted Lorenz?
Which one?
Slide, I don't know, it's 15, I think.
Yep.
Yes. Can you explain to me how how should I read this? What is it good performance on the FPGA?
Yeah, you can see. So, this is the line. The lines precisely match, right, from the actual Lorenz attractor data points with the FPGA prediction. So it's perfect until the time step 300. Here you see that they completely go over. So yeah.
Okay, all right, and that's expected, I guess.
And this is just X, Y, and Z axis from the Lorenz attractor.
I mean, would you not want to match perfectly even after the initial phase, or?
I'm sorry.
Would you not want them to like match perfectly regardless of how long it takes, or I guess I'm not seeing the part after like the 400, I guess, time step that it start to get out of phase or whatever that the disagreement.
If I want to have it, yeah. I want to have it matched every single time step,
okay.
right? Yeah.
All right, but that's what you have.
But it's not what happens because the model is very simple and
I see,
small.
but I guess your point here is that it's the same between FPGA and CPU. Like I see both of the cases.
It's exactly the same thing. That's the thing, right? Because it was like, okay, does float 32 make any difference? Of course not. I mean,
okay. All right, thanks.
Yeah, but then explore further quantizations to see how it actually performs. Yeah.
Yep.
I have a question about the reservoir computing. If I wanted to replicate your model,
yep.
Would I have to copy it from you, or is there a way to copy exactly what's going on inside the reservoir computing?
The code for this model, I mean, or
any model.
Yeah, I think we're about to publish, if not published yet, there's a package which deals with lots of types of reservoir computing methods. It's going to be open sourced, I believe, if it's not yet, called SCAN. And SCAN, S-C-A-N. And there you can see how these models are implemented. Yeah. And then, of course, to transform this to Verilog, then that's another topic. Yeah. Okay.
Okay, any other questions? Okay, don't see any, so thank you again.